Have you ever just stopped and looked at your phone or your laptop and wondered how? How does this thing actually work? Well, it turns out our entire digital world, every single bit of it, hinges on one ridiculously important idea from physics. And it's all about something called a band gap. I mean, think about it. Why silicon? Out of all the elements on the periodic table, why did this one material become the absolute foundation of everything we built? What's so special about it? The answer is, well, it's both way simpler and way cooler than you might think. Yep, that's it. A gap. A tiny, little forbidden zone where electrons just aren't allowed to go. If you can wrap your head around this one single concept, you'll unlock the secret to how we control electricity, and in doing so, how we control information itself. So here's the plan. We're going to start in the electrons playground, see how these energy bands get created in the first place, and then understand how that gap defines literally everything. After that, we'll see it in action, making light and power, and we'll finish up by looking at how we're actually engineering the perfect gaps for the future. All right, first stop, you see, the magic trick behind all electronics, the absolute core of it, is control. To build anything useful, you have to be the boss of electricity. You got to tell it exactly where to go and, more importantly, where not to go. And really, that's the whole game. The genius of a computer chip isn't just about letting current flow. It's about being able to stop it. It's the ability to turn that flow on and off billions of times a second. It's about creating superhighways for electrons right next to dead-end streets. So how do you build those highways and dead ends? Well, materials do it naturally, and it all starts when you take trillions of lonely atoms and convince them to come together and form a giant, organized city made of crystal. Okay, so picture just one single atom floating in space. Its electrons can't just have any random amount of energy. They have to live on very specific, distinct energy levels. You can think of it like a single house with different floors. An electron can be on the first floor or the second floor, but it can't hover in between. But here's where it gets wild. When you bring billions and billions of these atomic houses together to build a crystal, their individual floors start to influence each other. They blur and merge together, creating these huge, continuous energy bands. It's like all those separate houses have suddenly formed a massive city, with entire neighborhoods where electrons are allowed to hang out. Now, in our new electron city, there are two neighborhoods that matter most. First, you've got the valence band. Think of this as the suburbs, where all the electrons live. They're pretty much locked in place, bound to their homes. Then, above that, you have the conduction band. This is the city's freeway system. If an electron can just get enough of an energy boost to jump up to this freeway, it's free to zip around and carry an electric current. And check this out. This isn't just a convenient story we tell. It's real physics. This is what quantum mechanics actually predicts. This chart shows the possible energy an electron can have inside a crystal. You see those breaks in the curve? Those are the gaps. Physics itself says there are forbidden zones where no electron is ever allowed to exist. And that gap is everything. Seriously, the size of that forbidden zone between the suburbs and the freeway is the one thing that determines if a material is a conductor, an insulator, or something else entirely, something special. So let's put a pin in it. The band gap is basically the price of admission. It's the toll an electron has to pay to get from its quiet home in the valence band up to the fast lane of the conduction band where it can actually do some work. This table just lays it all out perfectly. On one side, you've got conductors like copper. Here, the bands actually overlap. There's no gap at all. It's like the freeway runs right through the suburbs. Electrons can just cruise around whenever they want. On the other extreme, insulators like diamond have a massive gap. The toll is just way too high. Electrons are completely stuck at home. But right in the middle, you get the Goldilocks material, semiconductors like silicon. They have a small, just right gap. Normally, electrons are stuck. But if you give them just a little nudge of energy, they can make the jump. And that ability to switch, that's the secret sauce for every transistor ever made. Okay, so being able to switch current on and off is a pretty big deal, but it gets even cooler. It turns out by managing this little jump across the band gap, we can actually create light out of thin air and even turn light back into electricity. Take an LED, for example. What we're doing is forcing a bunch of electrons up into that conduction band freeway. When one of those electrons inevitably falls back down across the gap to its cozy home in the valence band, it has to get rid of that extra energy. So it spits out a little particle of light, a photon. And here's the magic part. The color of that light depends entirely on the size of the drop. A small drop, a small band gap, gives you low-energy red light. A bigger drop gives you high-energy blue light. It's that direct. A solar cell? It's just an LED running in reverse. It's incredible. A photon from the sun flies in and smacks an electron chilling in the valence band. If that photon has enough energy, at least the cost of the band gap, it boots that electron all the way up into the conduction band. Now you've got a free-moving electron. And if you collect all those newly freed electrons, you get an electric current. Light in, electricity out, all thanks to the gap. But there's a little wrinkle here. See, the way an electron falls across the gap matters. In some materials, called direct band gap materials, the electron can just drop straight down. It's a clean, efficient fall that releases a nice, clean photon of light. But in other materials, like our friend silicon, it's an indirect band gap. The electron can't just drop straight down, it also has to kind of move sideways. It's a clumsy, awkward fall, and most of the energy gets wasted as heat instead of light. And this right here answers a question that pops up all the time. This is it. This is why we can't make a good laser out of silicon. It's just not built for it. It's fantastic for making switches, but because it has that clumsy, indirect band gap, it's absolutely terrible at making light. And you can see it all in the numbers here. We measure the band gap in a tiny unit of energy called an electron volt, or EV. Look at silicon. Its 1.11 EV gap is just perfect for transistors and solar cells. Gallium arsenide, with a slightly bigger gap of 1.43, gives us our classic red LEDs. And then you've got gallium nitride with a whopping 3.4 EV gap. That massive drop is what finally made bright blue and white LEDs possible. You see, the band gap isn't just some random number, it's a blueprint. Which brings us to the final piece of the puzzle. And this is where things get really futuristic. For most of history, we were basically prospectors, searching for materials that happened to have the band gap we needed. Not anymore. Today, we build them to order. The field is called band gap engineering, and it's exactly what it sounds like. It's the art and science of deliberately designing a material to have the exact band gap you want for a specific job, whether it's for a super efficient new solar cell or a laser that operates at a very specific color. And the techniques are just mind-blowing. Scientists can mix and match elements to create custom alloys. They can literally build new crystals, one single layer of atoms at a time. They can even take tiny nanostructures and physically stretch or squeeze them to fine-tune their band gap. We're not just finding materials anymore, we are becoming atomic architects. So there you have it. We started with a simple piece of silicon and ended up here. This one simple idea, this forbidden zone for electrons, is the secret ingredient that allowed us to build our entire modern world. We harnessed it, we engineered it, and now you have to wonder, what new worlds, what new technologies will we build with the perfect gaps we're only just now learning how to design?